After receiving the DCI, UE successfully located its PDSCH on the resource grid. We know where the PDSCH is located, but have you ever wondered how these resource elements became the PDSCH? The PDSCH is not created by directly placing user data onto the resource grid. Everything begins with the transfer block inside the base station. From there, the data passes through a complete processing chain before finally becoming the PDSCH. Inside the base station, many packets are waiting to be transmitted to the user. Scheduler decides which packet should be transmitted during the next transmission interval. These selected packets are grouped together into one larger unit, which is called the transport block. This transport block now represents all the user data that will be processed by the transmitter before being sent to the UE. Every transmission starts with this transport block. Scheduler has now selected the data to be transmitted. This collection of information is called the transport block. A transport block is simply a sequence of bits. These are the actual information bits that will pass through the transmitter processing chain before being mapped onto the PDSCH. The size of the transport block is not fixed. Sometimes it is small and sometimes much larger, depending on the scheduling decision, available resources, and the selected modulation and coding scheme. Regardless of its size, every PDSCH transmission always begins with one transport block. Before transmission, base station must make sure that the receiver can detect transmission errors. Now the transport block is passed through a CRC generator, which computes a checksum from the transport block. This checksum is appended at the end of the data. As a result, the transport block contains both the original data and the CRC. Later, the receiver performs the same CRC calculation to verify whether the received data is correct. After the CRC is attached, packet is transmitted through the wireless channel. Two outcomes are possible. If the packet arrives without errors, CRC matches perfectly and the UE accepts the transport block. But even a single bit changes during transmission, CRC immediately fails. This is why CRC is such an effective error detection mechanism. Even a single incorrect bit is enough to trigger a CRC failure. After CRC attachment, transport block is ready for channel coding. Can we directly feed it into the LDPC encoder? Not always. LDPC encoder only supports a limited code block size. A larger transport block simply cannot fit. Instead, the transport block is divided into multiple smaller code blocks. This process is called the code block segmentation. Only after segmentation, each code block can be encoded independently using the LDPC encoder. Transport block is divided into multiple smaller code blocks. Each code block can now be processed independently by the LDPC encoder. Remember, transport block already contains one transport block CRC. After segmentation, every code block also receives its own code block CRC. Now each code block is completely independent and can be encoded separately by the LDPC encoder. This is the complete purpose of code block segmentation. After decoding, each code block is checked independently using its own CRC. Most code blocks may decode successfully, while one may fail. Instead of sending the entire transport block again, only the failed code blocks need to be retransmitted. This reduces decoding complexity and allows independent error detection and makes retransmissions much more efficient. Let's quickly review the processing chain so far. Everything starts with the transport block. A 24-bit CRC is attached to detect transmission errors. If the transport block is too large, it is divided into multiple code blocks. Each code block is now processed independently by its own LDPC encoder. In the next episode, we will begin with LDPC encoding and see how each code block is transformed into a protected code word.